Ah, insects, these small creatures that flutter around in our house and in our backyard. For a long time I've been interested in how these things fly, and it doesn't take much to understand why, especially once we take a look at them closely. This becomes abundantly clear once we see them fly in slow motion. When seen like this, some insects fly similar to a helicopter. They can remain fixed in space with only their wings moving through the air. Their motion goes from some kind of erratic blur to something very precise and almost robotic in precision. However, since there are many types of insects, there are many ways in which they can also fly. This is especially clear once we once again see the motion in slow motion. The flight now becomes more similar to, say, that of a bird, where there is a definite downstroke that pushes the animal upwards and keeps it aloft, and then an upstroke that just causes the wings to slide through the air. Once the insects gain a bit of speed, they begin to fly more like an ornithopter, in the classical sense, where the wings provide both lift and thrust, and you have something much more analogous to an airplane with a propeller. Let's take a closer look at the wing structure of an insect. We essentially have just a flat plate that connects to a joint. This joint acts something similar to a ball and socket, so it allows the wing to rotate in any direction. In some insects, this is especially clear, as the wing narrows down to a single point on the body, which is the ball joint. We can replicate this type of articulation in GMOD. With only two objects, one for the body and one for the wing, we can replicate the articulation by means of ropes and hydraulics to control the motion. The hydraulics are very long in order to simplify the math that dictates the length changes required in order to precisely control the orientation of the wing. By doing so, we can use simple sine and cosine functions that depend on a target angle to which the hydraulics will then expand and contract in order to reach that desired length. And as a consequence, the wing will rotate to that desired angle in reality. We employ a set of hydraulics to rotate the wing about the pitch axis about very large angles, meaning plus or minus 90 degrees. We employ a similar set of hydraulics to rotate the wing about the flapping axis. These are the hydraulics that ultimately drive the wing motion and lead to powered flight. We will also use a single hydraulic to rotate the wing vertically. This will allow us to mimic the folding motion of the wings. When we combine these three control degrees of freedom, the motion can become very similar to that of the slow motion footage. That is, the wing undergoes a figure-8 motion where it paddles through the air. The idea being that we rotate the wing at the end of each stroke so that it maintains a constant angle of attack and therefore generates lift in the same direction indifferent of the direction of motion. So what can we do by being able to control the wing to this extent? Well, here's an example of a machine that flies just using two wings, and through them it achieves control about every axis and about every flight attitude. It can take off and then maneuver in every direction. For clarity, let's just see it take off vertically. It can hover with full control and without any problems. It also has robust and authoritative control about the roll axis. The pitch axis is much the same. It's a little slower, but overall it responds very well to abrupt control inputs. Finally, we can control the yaw axis in a similar fashion. It's not as fast as the other two axes, but it responds fast enough in order to, well, rotate the aircraft to a different heading. When we put all of this together, we gain an aircraft that can not only hover, but can also translate and maintain horizontal level flight. The transition between both states is accomplished seamlessly, and there's no obvious fixed point when the aircraft begins to fly one way as opposed to the other. And all of this is accomplished with nothing more but 2 wings and a fuselage, which builds upon its inspiration of insect flight, where these animals achieve similar flight with a similar mechanism. To accomplish this type of control, we can consider level and horizontal flight to be different conditions. When the aircraft is hovering, we can control the pitch axis by changing the average dihedral angle. This offsets the net thrust generated by the wings, and we get a torque. To control the roll axis in a hover, we can simply change the amplitude of each wing, such that one wing has more amplitude than the other, and that causes the aircraft to rotate. For the yaw axis, we can simply bias the angle of attack of each wing, such that it bites into the air at a slightly different angle. In level flight, we need to control the wings differently in order to achieve the same control output. For the pitch axis, we now sweep the wings back and forth about their folding axis. This will shift the center of lift of the wings relative to the center of mass and will cause the aircraft to rotate. It's a bit easier to understand this control scheme once the wings are flapping. To rotate the aircraft upwards, we simply sweep the wings forward, and to rotate the aircraft downwards, we sweep the wings backwards. This causes a weight shift effect, and the aircraft rotates accordingly. To control the roll axis about level flight, we simply apply a motion similar to ailerons, where one wing creates more lift than the other, and this causes the aircraft to rotate in the direction of the least amount of lift. We can also see this as swapping yaw control in a hover for roll control in level flight. If we see the roll control in slow motion, we can appreciate how one wing has more angle of attack during the downstroke than the other, and conversely this dynamic reverses in the upstroke, where one wing now has less angle of attack than the other, and the net effect is that one side always has more lift than the adjacent side. For yaw control, we simply apply differential amplitude, where one wing produces more thrust than the other, and this causes the aircraft to rotate. We've essentially swapped the roll control in a hover to become the yaw control in level flight. We can shift between both of these control configurations by measuring the local acceleration. When the aircraft is hovering, we know that the acceleration vector will be oriented with the nose of the aircraft. However, once the aircraft begins to pitch forward, the acceleration vector will be oriented at a different angle to when it was in a hover. Since the instantaneous acceleration of the aircraft changes with time, we need to filter out the long-term acceleration. We can do this by means of a low-pass filter, where we ignore the high-frequency oscillations caused by the flapping wings. We can see an implementation of a low-pass filter in action by oscillating the fuselage back and forth and visualizing the filtered acceleration at low flapping frequencies. Both vectors will align very closely. As we increase the frequency, the low-pass filtered acceleration will begin to lag behind the instantaneous acceleration. It will also tend to remain more horizontal and aligned with the gravity vector. As we continue to increase the frequency, the low-pass filter really kicks in. The instantaneous acceleration is very wild and oscillates everywhere, while the low-pass filtered acceleration remains very closely aligned with the gravity vector. Ultimately, this means we can use the low-pass filtered acceleration as a guide in order to mix our controls. We can better understand this control mixing by witnessing the acceleration and velocity vectors in real time. As expected, the low-pass filtered acceleration is much more stable than the instantaneous acceleration. as the instantaneous acceleration is acutely affected by the oscillation of the wing. When we rotate the aircraft forward, it will slowly gain velocity, and the acceleration vector will remain roughly vertical. As a consequence, we know the control inputs need to mix slightly between the hover condition and the level flight condition. This mix will become more biased towards the level flight condition as the angle increases and the aircraft ultimately is flying horizontally. Since we are ultimately accomplishing weight shift about the pitch axis, the control deflections are inversely proportional to the acceleration, meaning that under large accelerations the deflections are smaller, and under small accelerations the deflections become very large. This is especially important in horizontal flight. In these situations, the pitch deflections might even have to reverse because the aircraft for an instant begins to experience negative Gs rather than positive Gs, since the wings can unload if the aircraft pitches down quickly enough. Due to how the mixing occurs, there's no preference for the actual orientation of the aircraft. That means it can be rotated backwards and fly upside down, and the controls will be just as effective. A particular case when it's especially obvious that the orientation and magnitude of the acceleration determines the control deflections is when the aircraft decelerates from level flight and goes into a hover. Moreover, the pitch control system will also work when the wings don't flap, since it's ultimately just dependent on the net lift they create. As a consequence, the aircraft can also glide without any change to its control scheme. The only drawback is that it loses yaw control, since it no longer has access to asymmetric thrust. We can gain a better appreciation of how the entire system works by simply watching the aircraft flying. As mentioned before, once the aircraft gains airspeed, it can enter a glide very easily. It merely stops flapping its wings, and the control system will work just as effectively as if it was flapping them. Please note that the stability of this aircraft is being augmented by means of a PID controller. This is especially important about the pitch axis, since in horizontal flight, the aircraft is either neutrally or completely unstable due to the way it controls pitch. Therefore, the pilot is not directly flying the aircraft, but really just telling it at which rate it should rotate. We can gain a better appreciation of how the wings move by filming them in slow motion. We can also add a trail to their path to visualize how they cut through the air. This is especially informative in a transition state where the aircraft isn't exactly in a hover, but it's not exactly flying forward either. Here we can see how the angle of attack of the wing changes drastically between the upstroke and the downstroke, and how the lift force and the thrust also mix together to maintain the aircraft aloft. As expected, the wings have to produce more lift during the downstroke and less during the upstroke when the aircraft is in level flight. This can be seen by an asymmetric angle of incidence when the wings are flapping. In slow motion, we also gain a much better appreciation for how pitch is controlled in level flight. The wings sweep forward to pitch the aircraft forward, and they sweep backwards to push the nose down. Overall, this aircraft gives us an insight into the complexities of insect flight and how we might mimic it.